So I would like to go over chapter 9. Chapter 9 is about inferring population means. You learn deeper how to try to guessing um, the process of the mean. So right here, I'm trying to finish 3 sections at a time, but let's see the time. So section 9.1 is about sample means of a random samples. Sample mean notation as X bar, like I introduced before already. But you will see later more notation on sample means later. So in this section, we will discuss the accuracy and precisions of the sample means as an estimate of the population mean. Population mean notation for this as a mu, right? Okay. Sample mean notate as X bar. And you will need to find the standard error of the sampling distribution of the sample mean. Okay, so already we will focus on this too. It's more like kind of like the activities for us to recognize accuracy, precisions, probability distributions, and then later you will see the actual application for this chapter 9. So notation review, as you can see at the below. This letter M kind of is notation for mu. That's a population mean. Okay, we read as mu. And below that is X bar. This notation for sample mean. So X bar will be estimate for mu. In other words, sample mean, X bar, will estimate for population mean, mu. The third one is sigma, population standard deviations. We have learned sample standard deviation S in chapter 1. So sample standard deviation S will help us estimate population standard deviations, sigma. Okay. And another word, we got different rows for mu and sigma. So they are called perimeters. Okay. So let's go deep into the activities here to identify accuracy and precisions of the sample mean. So usually sample means is unbiased when estimating the population mean. So on the average. So the sample mean is the same as the population mean. It's said like that it's not really like exactly the same, but like I said, sample mean represent for a small group. Okay, small group, the mean of the small group, the average of the small group. But the population mean will be talking about a bigger group, very huge group, the average of the huge group. So if we compare sample mean with a population mean, of course, population mean will be more accurate than the sample mean. Okay. So however, like sometimes you cannot take a large group to compute, like to do investigating on that group. So we try to get just a small group and, take the average or do computation so that we can estimate for the entire group, which is the population. So the precisions of the sample mean depends on the variability in the population. So variability is here, they're talking about the standard deviations, how spread out the data based on the graph, based on the data they've given us. Usually for this introduction class, they provide us the graph. That provide us things to look at and estimating it. Sometimes they did for us already. They give you a value for standard deviations. So you just use that to compute directly in the work and make decisions. So the more observations we collect, the more precise of the sample means becomes. That's true, right? Sampling distribution of the sample mean. So sampling distribution is talking about a lot of data combined and make it become a distribution, become like a graph. Usually this type, when the data, gather together, we collect a lot of data together, they will form a bell shape. Okay? The sampling distribution can be thought as a distribution of all possible sample means that would result from drawing repeated samples from a certain size from the populations. So it looks like this definition is kind of a bit, broad, right? So later you see the pictures, like I said, they try to stick all of this together. If you are if we are talking about like sampling distribution, like it looks like a bell shape. Plus here they explain, you can thinking of all the sample mean of many small groups. They combine, okay? But they do repeating the sample of a certain size, same size. Reminder, the standard deviation of the sampling distribution is called a standard error. Okay. The standard deviation here is like you can thinking of small s or sigma of the whole distribution. And they call this as a standard error. It's kind of a different name to apply into this chapter. Effects of the sample size on the sample distributions. So in general, they want us to know the more data, okay, the more data we have, the better. So it's helping us to estimate things better. As the sample size increases, the standard error, which is the standard deviations, will decreases. But the mean will remain the same. And they show us the picture like this. You see, n is 100, will look like that, right? The data is kind of in between 85 to 90, right? When the sample size is 400, you see that the standard deviation looks like smaller. You see that? It's just exactly the same 3 graph, but the picture, the first one, you can see the standard error is kind of bigger. The second one is smaller, a bit smaller. But the third one is n is 900, n which is the sample size, which is the sample of the data, 900 data. And you can see they stick together and it make the standard error or the standard deviation very small, which is good. So all of this, when we are formed, look like all of this will be normal, which is look like a bell shape. The accuracy and bias of the sample mean. So they said for all populations, the sample mean, if based on a random sample, is unbiased when estimating the population's mean. And the standard error of the sample mean, they given us the formula is sigma, which is the population standard deviations divided by the square root of the sample size, n. So this is the standard error. The standard error, because for the sampling distribution all the time, we are based on the size. So they will provide us the standard deviations, but they also provide you a number of the data so that you can compute the standard error. Like you see the picture above, right? The sample size increases, they really care. The more size they increases, the better. The standard error is going to be smaller, will be good for us to compute. As the sample size increases, the sample mean become more precise. That's the conclusion. So now let's do an example. Playlist. Okay. So let's take a moment reading this on your own. And please think about the question A. Okay. So the question A asking, is the mean value of 258 seconds a parameter or statistics? Oh, okay. And explain. So I just want to repeat again the word parameters. They're talking about the population mean or population standard deviations, which is mu or sigma. And our statistics here is a new name for sample mean and sample standard deviations, S. Sample mean is X bar. So they want us to recognize what is the letters, what is the term 258 seconds stand for. Okay, so for a second, you can see that the mean value, because they're just talking about like, you know, a student has a large digital music library, right? So the mean length of the songs, of all the songs, most all the songs, is that amount, with a standard duration is 87 seconds. So the student creates a playlist that consists of 30 randomly selected songs. So you can see the number that you are having is the entire like the digital music in the library, the mean of all of it look like is 258 seconds, and go with the standard deviation is 87 seconds. For the second sentence, it said the student creates a playlist. So it's here is like the smaller group, right? Consists of 30 randomly selected songs. So here the conclusion, the mean value of 258 seconds is a parameters, because it is mean of the population is all of the song in the library. Agree? So part B, what should student expect the average songs length to be for his playlist? Because he pulled out like 30 of them. So the student should expect the average songs length of the playlist is 258 seconds. The sample mean is typically the same as the population mean, right? So if they take the average is all of the entire like playlist is 258, the average is like most of them. So when you take out 30, it look like around 258. It can be 256, right? But look like it's close to that value. But N is like 30. So let's see how many seconds. Instead of the standard error of for the entire is they given us is I think 87 in the right in for the standard deviations. So they want us to find the standard error of this. Then what you're gonna do is to find the standard error, you got the value, standard deviation sigma divided by square root of n. Square root of n is actually helping you to see if the size is okay. So in this case, the size is 30. So we compute is the standard error is about 15.88 seconds. Like the spread out between each songs, each playlist from the mean. So part D, would a playlist of 50 songs have the standard error that is greater or less than your answer for part C? So if you want to know this, you will replace 50, replace for 30, okay? And you will find a value. So the size is increasing. I believe the standard error will be getting smaller. You can try on your calculator. So the answer is if the playlist has 50 songs, the standard error would be smaller because the standard error decreases as the sample size increases. So that is the content for 9.1. So let's see if anything in 9.2. 9.2, you learn about central limit theorem for sample means. Central limit theorems are the requirements before you are doing the work. You are inferring the mean. So they have rules, but very simple rules. You can check quickly. So we will apply the central limit theorem for the sample means to calculate probabilities and describe the features of the t-distribution. So now they're talking about the t-distribution coming in. So 9.1, you're talking about the sampling distribution, right? It's all the sample mean, right? So now it's the t-distribution. Let's see what they're talking about this. Let's look at the central limit theorem first. If certain conditions are met, so what are conditions? So you will see later, there's 3 of them. So the central limit theorems asserts us that the distributions of sample means follow an approximately normal distributions, no matter what the shape of the population distributions. So it's mean, right? It's obviously is when you check the central limit theorem requirements, it's okay to make that distribution become normal distribution. And why? So if we're using that, the normal distribution, and normal distribution, we're talking about a bell shape, so that we can easier compute by running StatQuench. Okay. Sometimes people will convert normal distribution, go back into, we call it another name. We call it a standard normal distribution. It means you need to convert all the population mean and the standard deviation we compute somehow. And the z-score will be evolving as well. But to make things easy, I will teach you run StatQuench so that you can quickly get the point for this chapter 9. I try to run StatQuench later if there is any like example or direction need us to run StatQuench. So for all the things that they're talking about the central limit theorems, mostly central limit theorems coming in when we are testing the distribution like the we call the sampling distribution, or we're testing for the sample mean. Okay. I will let you know when you need to check it, and you know right away. So mostly it's happened in chapter 9. I think from chapter 8 as well. Okay. You can go back chapter 8 and check that. We're talking about hypothesis testing. So here, let me see. So when determining whether you can apply the central limit theorems to analyze data, consider these 3 conditions. The first one, random sample and independence. What does it mean? It means each observation is collected randomly from the populations, and observations are independent of each other. You have learned this independence, right? They're not related to each other, not affected of each other. So each observation is a different things. Second, large sample. Either the population distribution is normal or the sample size is large. So usually they want you to have the sample size n is 25 or above. Okay, we're checking that. If it's smaller, then it will be something else. Okay, so the third one is a big populations. So for this one, you only need to like get your sample size and time tens. I think it's just simple. So if the sample is collected without replacement, then the population must be at least 10 times larger than the sample size. Okay. So this one, you can see the example below. I'm not very like strict on testing it, but if they do, then it's very obvious for you to see it. So the central limit theorems. So just pretend if the 3 conditions are met, then the sampling distribution of X bar, which is all the mean, all the mean of the small group, they combine all together, make that as the distribution. We call normal distribution, and they approximately is capital M, stand for normal, parentheses. You got mu, stand for the population mean, commas, and we got the standard error, which is the sigma divided by square root of n. Okay. Just here is the notation only. It's not, you're not going to do any work yet. So the larger the sample size, the better the approximations all the time, right? So if the population is normal to begin with, then the sampling distribution is exactly a normal distributions, regardless of the sample size. And here is more scat about visualizing the distribution of the sample mean. So it looks like it's not really about bell shape yet, but we're trying to convert that into the bell shape. See here. So we got 2 graphs. One graph, the size and is 30. Another graph is 90. So look, we compare, 90 is more better looking at the blue one, right? It's more like the bell shape than the other one, even though they both call the normal distribution, they both call bell shape. It doesn't have to be like perfect. However, the more sample size, the better. So the example weights of the 10 years old boys, let's check this out. According to data from the National Health and Nutrition Exam Survey, the mean weight of 10 years old boys is 88.3 pounds. Okay, if the standard deviation, which is either sigma or S, right, of 2.06 pounds, so we assume the distribution of weight is normal, which is they taking many group of boys, they all weighing they all weight in the same pounds, like 88, 87, 89, stuff like that, and got, the same standard deviations for if they got the sample size of the boys is just the same. But if the size, the number of the boys that it make testing bigger, then you will see the standard deviation will be changing. But the mean is still the same. So not make things complicated. So let's check this out, the question. Part A. Suppose we take a random sample of 30 boys this time. So from the populations, can we find the approximate probability that the average weight of this sample will be above 89 pounds? So how do we find it? If not, explain why. So above 89 pounds, you mean like all the boys, like you will find a probability that the boy just above 89 pounds. But the average is 88.3 pounds. The standard deviation is 2.06 for all the kind of the average for the boys. And if we specify the boys, the sample size of the boys is only 30, then what happens? So we can do by hands, or we can run StatQuant, or we can using TI-84. So before this, it looks like we need to analyze if this met the central limit theorem. So check this. So first we have the random sample, yes, or independence. Population is at least 10 times larger than the sample size. And the population is normal. So they're just saying like that. They don't write it down. So if we really do not care step by step like here, because usually they don't test that. So let's pretend this too. Let's pretend that already met the requirement. So what is the quick way to doing it? Do we have answer right here? Let me see. Okay, let's do this. I'm gonna run StatQuant real quick to see what happened. Okay. So first you can compute by hands with 2.06 divided by square root of 30. So what is it? Then I will run it. So I will log in StatQuant right now for you to see it. To find the probability. Because the look like they don't give you the answers. StatQuant. Log in. Open StatQuant. Okay, so in order to run StatQuant, I go to Stat. I go to calculators, and then I go to all the way to normal. So we have this graph. Let me see. So the mean that we are having is $88.3. I type it in. For the box for standard deviation here, I'm not gonna write the standard deviation only, but I will figure out the standard error, which is I'm gonna use my calculator on my hands. I'm having, let's see, square root of 30. Square root of 30, so is 5. So you don't have to write to 100 times right now. Just write to 1,000 place. It's more accurate. So 5.477. Let me write it down. annotate. Root 30 is 5.477. So I'll choose that value. So now I'm gonna check. So the standard error is 2.06 divided by 5.477. So I'm gonna get this value. I'm having 0.376. The more number you get, the more accurate. But I'm taking the thousand place until the answer is you know, we got the answer for to finalize all of this. You route to 100 place. So I'm gonna have 0.376. Let's see what happened. Click that in. So right here, they're talking about larger. So I choose the size larger to, you said, is it 89? Let me check back. 89 pounds. So let's click compute. So we are having the probability is we found on StatQuant is 0.031, right? And blah, blah, blah right there. So here is like 3.1%, right? You multiply by 100%, you're gonna get the value in percentage. But like I said, it's okay for me to show me all of this picture, including with the answer right there, then that's fine. This is talking about the right tail, the right tail, the right tail. So the right tail, the left tail you learned from chapter A. You can check that. So this is the right area. So this is the value. Okay. Let's go back to this part A. So part B. They're asking, suppose we take a random sample of 10 boys from this population. So can we find the approximate probability that the average weight of the sample will be above 89 pounds? So let's try this, okay? So we have a random sample. The population is at least 10 times larger than the sample size. The population is normal, so we can apply the center limit theorem even though the sample size is less than 25. So you're gonna have similar. So what is the value? Oh, it looks like right here is the answer for part A. Is that right? Yes, it is. So they having the standard error. They take the standard deviations divided by the square root of 38. They got a value is 0.3761. They plug that value and put in this box. They put 88.3 in that box mean, and they choose the size for greater than because we're talking about greater, right, larger than 89. So we have this value, and we are having like this value that we've just run. I just run StatQuant for you to see it, and you are having the probability that of the sample is greater than 89 pounds is about 3% or 0.03. That's part A. Let's say part B. Part B just similar, exactly similar steps. You compute this value out. You can see the probability is bigger. So that is the standard error is bigger. Plug it in. Just similar things. Now you got 0.14127 blah blah blah. This is the value of probability. When you convert this out, you are having, you multiply by 100%, you got 14%, 14.1%. So the probability the sample mean is greater than 89 pounds is that value. So what does it say? So this probability is different than our answer to part A due to the larger standard deviation in the distribution size. So it looks like if the size is small, the less accurate that you're going to have. Similarly, with different example, is about home prices. Home prices is in a certain community have a distributions that is skew right. You can imagine skew right, like less data on the right side, like this. More data on the left. Let's skew right, skew right. The mean of the home prices is $498,000, with the standard deviation is $25,200. So part A, suppose that we take a random sample of 30 homes in this community. So what is the probability that the mean of this sample is between 500,000 to 510,000? And again, we do similar way. We check for the standard error. You see the mean is right there. It's 498,000. 498,000, right? With the standard deviation right there. We have the sample size. You're gonna take this 25,200 divided by the square root of 30 and plug in run StatQuants like we did for the previous example about the boys, the 10 years old boys, and run StatQuants just exactly the same to see if the mean is between these two. Please practice. So we quickly check the central limit theorems. We got the random sample, right? The sample is large. The study is greater than 25. And the population is large. We assume that there are more than 300, assuming we just take the sample size 30 times 10. So we have the central limit theorem we met. And we have this distribution is normal. We've got this notation. And we are doing similar with previous example. So let's check out with part B, then we can see the solution and how they run it. Suppose we take a random sample of 10. It's similar, right? Similar to example about 10 years old boys. So here they run StatQuants. We got a standard error by taking that value divided by square root of 38. We have 4,600.87. You put in that box. The mean is 498,000. 498,000, right? And you got a standard deviation right there. You got the value. Here is we're talking about in between 500,000 with 510. So there's two boxes. So instead of standard, I'm gonna do it for you. Would you see it? 489. See that? So let's do another one. So let's do between. Click between because we're talking about the area in between. So click in here. 498,100. And this value is from 4600.87. And here is from 500,000 to 510,000. Click compute. We have the probability is 0.327339 right? This is middle area. So you take the screenshot of the whole thing or copy and paste the whole thing to the like this, like they copy on the sign and then they combine to make a document. The code is the same. See? Identify the distribution. The next slide shows 3 distributions. So one of these distributions is the populations. The other 2 distributions are approximate sample distribution of the sample means randomly select sample from the population. So one of the sample size 10 and the other of the sample size 25. So look at 2 examples. You can see they're using the same, I think sample size of 30, right? So they're a bit right there. I think it's 30, it's supposed to be 30. So in general, they're telling us the sample size really affects the probability, okay? But in this many days, like the more sample size, the larger sample size that you have, the standard deviation will be small. And this will help you to figure out the probabilities is more accurate. So this one is, you see there's 3 shapes, right? So what is the question that asking? Identify this. The central limit theorem tells us that the sampling distribution for sample means are approximately normal. So this graph looks like it's not normal, right? It's not the best shape. Then what happened? And the next one, figure A and figure C, the sample size increases. The standard error, which is the spread of the distribution, decreases. So figure A look like has small spread. It means the standard error is big, right? Does the picture in green is have the standard error small. It looks like they have the bigger sample size. The blue one have the sample size of 10. Okay. Let me see. More spread than figure C. Figure A is the distribution of sample size 25, I'm sorry. And figure C is the distribution of its distribution for sample size of 10. Okay. But it looks like kind of not really helpful. Let me count. Is it 10, 2, 4, 6? It's more than that. I don't know why they said it's 10. Let me see over here. Okay. It looks like it doesn't make sense on the picture. It might be this part is not really important. They just want you to see this distribution is not normal. Okay. The important part on this is these 2 examples, home prices and the weights of 10 years old boys. These 2 are you need to practice over and over. And the next example about identifying distribution, you can ignore this part. It's not clear at all. So let's look at the t-statistics. What does it mean? The hypothesis test and confidence intervals for estimating and testing the mean are based on a statistics we call t-statistics. Okay, the t-statistic is where you do more work. You need to do more work. T-statistic is look like it's kind of a bit similar to z-statistics. So this one apply for we are computing by hands, right? So since the population standard deviation is almost always unknown, okay, so it means they will provide you the sample size the sample standard deviation S. They provide you this. The standard error that you learned in previously, they provide you this, right? The population standard deviations. So when they provide you a small s like that, and this we call still standard error anyway. But in this case, you will apply t statistic. So in order to figure out t statistic, we have to have sample mean x bar will be provided, minus mu will be provided, and all of this you have to compute that to get the t statistic. But no worry, we run StatQuant, so it's more easier than compute by hands. In this PowerPoint, they're showing us compute by hands, compute by T89, and compute by StatQuant. So, since the population standard deviation is almost always unknown, so we divide by an estimate of the standard error using the sample standard deviation S instead of sigma. So let's understand about t distribution or t statistics. The t statistics does not follow the normal distributions because the denominator changes with every sample size. The t statistic is more variable than the z statistics, whose denominator is always the same. So if the three conditions for using the central limit theorems hold, the t-test statistic follow a distribution called the t-distributions. So let's look at this, analyze this. The t-distributions is also symmetric and bell-shaped, like we just did earlier. Okay, we did the normal distribution. The normal distribution, we're talking about the z statistics, right? So here we're talking about t-distribution. They also mentioned about symmetric and bell-shaped, but you can analyze a bit. They're just a bit different. Is it normal? Okay, this graph. This is normal distribution. They're talking about the z statistics, but because we don't compute by hand, so we can ignore that. You just run StatQuant by two examples that I show you. And the second graph you see here, the t statistics, we got degree of freedom, which is df equal to 1 in this case. So the they will introduce us a bit about degree of freedom. What does it mean at the below, and you will see it's more clearer. Okay, it looks like it's 9.3 now. Again, if you have any question, please email me, let me know, and I will answer your question. Okay, since we're talking about that one, I think, let me see if I can go over 9.3 right now. We should go over 9.3 so that you will not getting confusing about t distribution. Okay. So in this 9.3, you learn about confidence interval as well. But it looks like, let me see, let's scan over it if they say anything about t distribution. Okay, look like no. Okay, so if they're not mentioned about that one, so you don't have to worry about it because it might be not for this class. They just like introduce us, the t distribution, how does it look like? The t distribution, like I said, is will be they provide us the sample size, the sample standard deviation only. So you using the formula, but I'm not gonna give you the test on the t distribution since it's not go deeper as we want it. So just ignore it, that part. Just focusing on the emphasized part that I should give you. 9.3 is also important on, you need to know how to compute the confidence interval for the population mean. Okay. So here's answering question about the mean of the populations. So there are two approaches for answering this question about the population mean. You're learning about how to compute confidence intervals by using used for estimating the parameters value. Parameter values right here, they're talking about mu. Another word is population mean. And two, we do hypothesis tests. Hypothesis tests we use for deciding whether a parameter's value is one thing or another. We check or not reject the null hypothesis. You learn a hypothesis test in chapter 8, right? So there are the same methods as introduced in previous chapters for population proportions, but modified to work with population means. For the confidence interval we did learn in chapter 7 already, so it will be more easier for you in chapter 9, right? Because you learned that already in chapter 7. It's just like repeating the steps, but it's just a bit different. Maybe they relate to some bit changing about the formulas. So confidence interval provides a range of plausible value for the population mean, along with a measure of the uncertainty in our estimates. And is a measure of the uncertainty in our estimates. The higher of the value of confidence, the better of your estimate is. If you're talking about confidence interval, we're talking about the intervals, right? So from where to where. Here we use confidence intervals whenever you are estimating the value of the population perimeter or mu on a basis of a random sample. They just like recommend us do not use confidence interval if there is no uncertainty in your estimate. But usually when you are doing work, the other time given us way to compute that. If you have data for the entire population, you need to find a confidence interval since the population perimeter is known and there is no need to estimate it. They give us a lot of definitions. You don't have to copy them all, okay? Just take the main idea. Before constructing a confidence interval for the population mean, you don't have to check these three because all the time they will give it to you enough. So let's do this example. A used car website wanted to estimate the mean price of a 2012 Nissan Altima. The site gathered data on a random sample of 30 such cars and found a sample mean, we call X bar, of 16,610 and a sample standard deviation, which is S, of 2,736. The 95% confidence interval for the mean cost of this model car is based on this data. They provide us the interval right there, right? They already give you the answers, but now we're checking it. Is it true or not true? Based on this data they provide you. The sample size, 30. The sample mean, 16,610. The sample standard deviation S, 2,736. And they want us to do a bit compute on 95% confidence interval to see what happened. So in part A, describe the populations. They want to ask if the value 16,610 an example of the perimeter or statistics. So here, if you understand the perimeter, is mean they're talking about the entire population. So look back here, we found a sample mean, right? Sample mean. This is statistic. Okay. They're not talking about populations here. B, they want us to verify that the conditions for valid confidence interval are met. Like I said, just obviously, you write the same sentence all the time, checking out of this three. Interpretation of the confidence level. So this is what I want you to interpret most of the time. So the confidence level is a measure of how well the method used to produce confidence interval performs. For example, in this case, a 95% confidence interval means that if we were to take many random samples of the same size from the sample populations, we all the time expect 95 of them would work. 95% of them would work. Contain the population parameters, and 5% of them would be wrong. Okay, not contain the population parameters. Calculating the confidence interval. So here they're showing us how to calculate the confidence interval in the section. So we're going to have estimators plus and minus the margin of error. The margin of error is a different formula, which is down here. To compute the margin of error, you are having the multiplier multiply with standard error, and the standard error we have different formula, which is equal to sigma divided by square root of n. See that? So we have like three different formula. We have the bigger formula right there, but margin error is right there. Margin error right there, and you have this formula for SE. So it means when you compute this first, this second, and go back to this third formula. Then we will differ with the exam from the example for us to looking at it. So, in other words, they would like to remind us the estimators here in this case will be X bar all the time. M stands for margin of errors. And T star, which is if we are having the, we're using that formula when, the T star here. We're using this when we are having the sample size S. If you're looking at the S in the prompt, the story, then you know what right away they're using T star. Otherwise, if they have sigma, then here they're using Z star. And where do you find Z star? Where you find Z star and where you find T star? I will show you. But remember this three formula for me, please. This formula and the above here formula here, they are the same, okay? So this formula using for when they provide you population standard deviations using this. So this still acts, this is still estimator can be X bar, okay, or mu. And we have the z star right here, okay. But usually they don't obviously write it down, but you can think of like I said. To construct or sample one sample t interval, you need 4 pieces of the information. You need a sample mean, right? Standard deviation S or sigma. If sigma, then you're using Z star. If it's S, then using T star. They have the table. I'll show you. The sample size, right? To compute the standard error. So for the multiplier T star or Z star is which you can look up in the table or use technologies. So T star is determined by the confidence level and the sample size. Okay, so that's the definitions. Using the confidence level and the sample size. The value of T stars tells us how wide the margin of error is. In terms of the standard errors, for example, if T star is 2, then our margin of error is 2 standard errors wide. No worry for Z star and T star right now. I will show you the table later. So when can be found using t-distribution table, but because most tables stop at 35 or 40 degrees of freedom, it's best to use technology to construct the confidence interval. So here is the example. We are having what? The data on speed is mile per hour, so random sample, 30, right? So n is 30. Cars traveling on the highways was collected. The mean speed is that, so we got x bar is 63.3. The standard deviation here, excuse me. So this says S. They don't write standard or population, so assume it's S. So now they want us to find 95% confidence interval for this mean. They want to find this. They want to estimate the interval for mu. All car traveling to verify that necessary is whole. Just similar to chapter 7, just a bit different is you look for more numbers. So here's the way we run StatCrunch. Like I just explained, use technology is better because it's more quicker, easier. I click accidentally something. 9.3. Okay, we are on here. So sample mean is 63.3. We did plot it out. Sample standard deviation is 5.223. This box, you type it in. Right, let's type it in for X bar, for S, sample size N, right? So this is, we're testing for, because this is S, so we're thinking about T distribution. So by running this, we go to one sample T summary, right? So later I will show you. And we have performed is the following. For hypothesis test, we're not going to do hypothesis test for now, maybe 9.4 and 9.5. Okay, so if it's that happen, then you click here and type in whatever the mean mu that they provided. But here we're not talking about hypothesis test, so ignore that part. We're talking about confidence interval. Then you check the level is 0.95. Technology already gave us the T stars in there. They compute that for us. And we are having the limit, the left limit and right limit. So here we call the confidence interval. Parentheses, comma, right? That's a confidence interval. Will be here. That's a conclusion. That's what I want that you will need to write on your test. Is that value? So let me close this. We'll choose that. Go to T-stat to running that example. So you run to T-stat, you go to one sample with summary, okay? With summary. We type it in. Type it in 63.3, maybe 63.3, 5.23. Sample size is 30. We're not doing hypothesis test, we're doing this. And you click compute. We are having the value is from 91.34, you can round up to 100 place, which is 61.35 to 65.25. Right? Write it down like this as a conclusion. You're done. And if you have any question, you can ask me, okay? So here's another way to using TI-84 to compute that confidence interval. For those who prefer this, then you can go ahead and do it. But I think because we are using StatQuant, you can just run StatQuant, it's fine. But if you're curious more, you can using by following the steps. So this is just similar, okay? We're estimating 95 that we just found for part B, and this interval as a conclusion. We all need to interpret this. We are 95% confident that the mean speed of the cars on the highway is between 61.35 and 65.25 miles per hour. This is what I need you to write for interpretation. The question C, is it plausible that the mean speed of the car on the highway is 67, and why or why not? So they're asking that if they based on part B, then you look at the value 67, is it in that interval? Look like no, it's out of the range, right? It's bigger than 65 on the right side. So it's not plausible, it's not believable. It's not plausible in our interval. Similarly, for example, for movies, just do the same thing. You can practice it on your own. Still run StatQuant like we do. Just enter in and you can see it. So this we're talking about 90%. Then you just type 90 in, not 95. Okay, so all of this you can practice on your own. It's just similar example. Again, if you have any question, please ask me. So we're done with 9.3. So next time I will record it 9.4 and 9.5 for you.